On some space missions, simple experiments were done to prove or demonstrate the physical behavior of objects in zero gravity. Here we launch a Gravitron to float freely in the cabin. It wants to spin about the wheel inside. To try and get it to tip over, the astronaut bumps it on the top and on the side, but it won't capsize. It's stable about the spin axis in which it was released. That's straight up and down. Here is the same configuration, one spinning Gravitron, but this time it's been oriented so the spin axis is pointing at the camera. Again, although it's been bumped on all sides, it will not tip. As before, it's stable about the spin axis in which it was released. This is a graphic illustration of the difference between a spinning and a non-spinning Gravitron. You'll notice the spinning Gravitron remains stable, whilst the other one tends to tumble end over end because it has no stable spin axis. If we watch it one more time, you'll see that one is spinning and one is not. The one that is not spinning just tumbles free, while the other one maintains the orientation in which it was let go. Now two spinning Gravitrons which are both stable as they spin. If we take one and bounce it off the other, you'll see that this time, because they're both stable, neither tumbles after they collide. Now a curious combination. Two Gravitrons attached together on a wiffle ball. They're both spinning in the same direction, so one would think they would be very stable in this configuration. But because they weren't perfectly aligned with each other, they got out of hand. Eventually, disastrous results. In slow motion, you can see how the misalignment causes them to break apart. But this time, the two Gravitrons are rotating in opposite directions from each other. And because their angular momentum vectors are in opposite directions, their stability axes cancel each other. So in theory, when we let the device go, it should tumble. Obviously, we can't make them both spin at exactly the same speed, so one of them is going to have a little bit of stability. But now we can bump the stack and make it wobble a little bit. As we bump it more severely, there is some tendency for stability, but not as much as a single Gravitron had floating on its own. So clearly, two Gravitrons spinning in opposite directions cancel each other. Now we're getting complicated. We have three Gravitrons all hooked up to the same wiffle ball. They're orthogonal to each other. That's to say, they're all at 90 degrees to each other. And this time, we're going to spin them all in the same direction with reference to their attachment to the wiffle ball. As we do this, you would expect the angular momentum vectors of each of the Gravitrons would add up to a single vector, which would be right between all three. As we release the device, you can see that the only axis it will rotate around is an axis that you could see if you put a pencil between all three of the Gravitrons. That is, an axis that is equidistant from all three of them. As it continues to spin up, by the natural character of the friction of the Gravitrons, it eventually begins to spin so fast that it comes apart. Here is the same combination again. Three Gravitrons mounted orthogonally to the wiffle ball. Once again, we're going to spin them all in the same direction. But before we do so, you can see how they tumble end over end. There's no stability there because none of them are rotating. Once the astronaut sets the Gravitron spinning, you'll notice that initially they begin to rotate around the same axis as before. But one of the Gravitrons comes off. And look what happens to the remaining two. They begin to rotate around a new axis, one that's right between the two. Again, they spin at such a speed that eventually the device falls apart. Here's an experiment that demonstrates how a non-spinning Gravitron behaves just like a ball on the end of a string. We can change the axis of rotation just as we could with anything attached to a string on Earth. But once we spin the Gravitron up, look how it maintains that stability around its rotation axis. We can spin it around and around, and it wants to stay in an orientation so that the spin axis is parallel to the axis of rotation to which the astronaut is holding the string. But when we change the orientation, Eventually, the Gravitron ended up changing the orientation of its rotation so that it matched the rotation axis of the string. This shows in a simple way how gyroscopes work.